Okay, so good morning, good afternoon. Good morning, good afternoon. It's a pleasure to present Jose Rodrigues from the University of Memphis. He's going to give a talk on the well-posedness and stabilization of a nonlinear structural-acoustic interaction problem. Thank you, Jose.
Thank you, Professor Luz. It's a pleasure for me to be here today and presenting this talk. Well, good morning, good afternoon, and perhaps good evening to those watching. Well, today I will talk about a model that we have been working lately, and the title of my talk is the following: on the well-posedness and stabilization of a nonlinear structural-acoustic interaction problem. This is a joint work with Professor Lashiewska. And wait, see, okay. So, well, it is well known that structural-acoustic models, they are really interesting. They have acquired the interest of many researchers nowadays, and also from the past. So, for instance, I mentioned here the works of Morse and Ingard. Also, we have more recently works like those from Banks and Smith, also Faru and Wang, and also Professor Lashiewska has a widely contribution in this area. For instance, in this lecture notes from 2002. So basically, our model has this kind of model. It has a lot of applications, and among of them, I'd like to mention, for instance, noise reduction in acoustic chambers, and also the pressure reduction in the cockpit of helicopter, for instance. So basically, the dynamics works as follows. We have this chamber or environment in which we have acoustic waves traveling in this environment. These acoustic waves, they interact with a border of this acoustic environment. So the border has two types of borders. One of them is supposed to be elastic, and therefore these acoustic waves, they will interact with these elastic walls, which will provide a feedback to the environment. So that's the basic dynamics regarding the model. So as an acoustic environment, we're gonna suppose we consider a bounded open set in R3, and the boundary is composed of two parts, gamma 1 and gamma naught. The portion gamma 1 is called hard wall, and the portion gamma naught is called the elastic wall. So in here we have two situations. We might have the case in which the elastic wall is flat, and the case in which the elastic walls are curved, so also known as shell problems. Okay, so our model here, our problem, our results focus on the case in which the elastic wall is supposed to be flat. For results regarding shells, curved walls, for instance, I mentioned here two of them. This work from Klingol, Lashiewska, Levitzik, and Zalesy from 2002, and also Daniels and Levitzik from 2008. Okay, so the equation that gives us the behavior of these acoustic walls obviously is given by a wave equation with Neumann boundary conditions. And as we can see here, we have dissipation term in the boundary, and WT denotes the coupling term, which will be coupled with the plate. So that's basically our model. The dissipation is supposed to act in the boundary. We have here a possible internal dissipation mechanism, but the interesting case is in the absence of this term. Okay. The dynamics in the plate followed is given by the following plate equation. So we have a 2D Kirchhoff-Boussinesq plate equation acting on the gamma naught portion of the boundary, which is the elastic wall. And as we can see here, we have a feedback, which will have the form of a damping term plus a nonlinearity F, which will be responsible to cope with both terms, which are this divergence here, and also this term which comes from the Boussinesq model. So as we can see here, we have non-locally Lipschitz terms, which is given by this divergence term, and also this term which comes from Boussinesq. It is known to cause blow up in finite time of solutions. So we have here two nonlinear terms which are competing between each other, and in order to cope with those terms, we have this nonlinearity F. So also we consider the three most common boundary conditions for the plate, which are clamped, simply supported, or free boundary conditions. Obviously, from an engineering point of view, free boundary conditions are more interesting. Is the most interesting type of boundary conditions. Okay. Well, a few comments. We know that it is known that this Kirchhoff-Boussinesq model, 2D model, is obtained as a limit of Mindlin-Timoshenko system, and computations on this limit are well explained and provided in this article from Professor Lashevska and Professor Shoshov from 2006. And as I mentioned, the interesting terms in the equation comes from the plate equation, which are this Boussinesq forcing term, and also the internal restoring force, which is the divergence. So when you combine those two, we have a global behavior of solutions. They dictate how the solutions behave. It is also known that there are some results in which similar models were considered. However, they consider some they have some regularizing effects, which is not our case here. So, for instance, in this paper that I mentioned here from Avalos, Lashevska, and Rebarber, we have they consider a model in which it has regularizing effects. Also, there are other works in which these regularizing effects might come from heat, if you consider heat dissipation, for instance, in the plate. Another interesting thing about this model is that the boundary dissipation in the acoustic medium is quite important, and plays an important role. It will gives us sufficient conditions in order to obtain strong Hadamard well-posedness, for instance. So here we are going to consider a few notations. We consider the natural phase space, the natural finite energy space for the system. This finite energy space is given by the space regarding the wave equation, and also the space regarding the plate. And depending on your choices for boundary conditions for the plate, we might have the following space H or for the plate. And the total energy, if you compute the total energy associated with system 1, 2, you can see that its expression will be given by number 3, in which we have the positive portion of the positive part of the energy, plus some nonlinear term that comes from the plate equation. Okay. In here, this capital function f is an antiderivative of our nonlinear source. And the positive portion of the energy is given by expressions 4 and 5 for the wave and plate, respectively. The form A is given by this expression depending on your choices for boundary conditions. So if you are working with clamped or simply supported, we have the traditional inner product coming from the Laplacian. And if you're working with free boundary conditions, we have some mixed terms, okay, where x1 and x2 denotes the variable in over the plate, which is considered to be like a plane, okay. Also, if you compute the derivative of this energy, you'll see that the derivative of the energy shows us that the energy is not quite dissipated. So as you can see, we have the presence of the Boussinesq forcing term. We shows us that the energy is not necessarily decreasing at first. So as we can see, there are many interesting issues happening with this kind of model. Okay, so our well-posedness results, I'm going to present the well-posedness results, and by a solution, I mean a weakly continuous function in which the time derivative of the acoustic waves, at least in the portion gamma naught, actually over the support of L, which is the localization function regarding the boundary dissipation, is supposed to be in L2. So also the system is satisfied in a distributional sense, and the nonlinear form given by the plate is given by this expression, okay, which is the nonlinear terms over the plate. Okay, so and also we can have strong solutions. Strong solutions are solutions which are more regular, which are continuous, especially for the plate with values in each wall. And also global, if we can extend this local time t for any arbitrarily large number. Another ingredient that we're going to use in order to obtain this global solutions is the following assumption on the nonlinearity f. So depending on your choices on boundary conditions, assumptions inequality 7 and 8 must be satisfied. And it is known that if your function f satisfies this kind of a relation here, in the case for p equals 3, for instance, so we can recover 7 for any value, for any delta arbitrarily small. And in the case in which eta of 1 is greater, it's a real number, then we recover the lower estimate for the antiderivative in the free boundary conditions case. Okay, so the main result regarding the well-posedness is the following. We've shown that for every initial data in the phase space, we found a solution, a local solution. Actually, we found a unique weak solution, local weak solution. And also, if we assume that the known explosion assumption 1 for the nonlinearity f, then we might extend these local solutions to global, and therefore at this point we can define this semi-group, nonlinear semi-group, which will be continuous in the finite energy space H, with respect to the weak topology Okay, so in this case, what we have is a weekly is a flow, which is continuous with respect to the weak topology. Okay. Also, it is the weak solutions will satisfy the energy inequality number 9. And here I denote the damping term by D. So at this point, we have this weak flow in the phase space. But it would be interesting to obtain a strong flow. So how do we do that? We need the energy identity. So in this case, we recover the energy identity in two particular cases. The case in which we do not have boundary dissipation, which is the case in which the function L is null, and the case in which the plate is containing the support of this localization function, which means that the boundary dissipation acts over the plate. So in those two cases, we can recover the energy identity, and therefore we can obtain a flow which is continuous with respect to the strong topology of H. Yeah, as I mentioned, at this point, once we recover the energy identity, we obtain a flow which is continuous with respect to the strong topology of H. Also, you can obtain strong solutions by considering stronger initial data, satisfying the following compatibility conditions depending on your choices of boundary conditions. Okay, so a few comments here. The energy identity for weak solutions is still an open problem. It's an interesting question that needs to be solved in order to obtain a flow which is continuous with respect to the strong topology for weak solutions. In the case, in a more general case, when the dissipation does not act only over the plate. A few comments on a few highlights in the proof. I'm not going to show the entire proof here. I'm just going to highlight the main points. The first one is the local existence is obtained by via Fayette-Galerki method, and this estimates on the nonlinear the terms that comes from Boussinesq, restoring the Boussinesq force are necessary, as well as the following Sobolev embeddings. And in order to obtain global solutions, assumption one on the nonlinearity F allows us to obtain the following lower estimate for the energy. And with this lower estimate, we can use standard arguments, Grongo inequalities, and extend solutions to any time t. Regarding the uniqueness, the step 3 would be the uniqueness, and in order to obtain this uniqueness, we adapt Sedenko's method, which consists on working on obtaining estimates for a solution for the difference of two solutions with respect to same initial data, but not in the phase space, but in a lower topology. So the main inequality, the main inequality that we want to obtain is the first inequality, in which this psi term is given by lower topology of difference of two solutions. Here, the operators A and script A are the traditional ones for the wave and the plate, depending on the boundary conditions. And also another ingredient that plays an important role in order to obtain the previous inequality is the following estimate of the nonlinearity. the difference of two nonlinear terms. Okay, so if we take the difference of two solutions for the plate, for instance, we have the difference of the nonlinear terms. This I call that M, and we need to estimate that in this fractional using fractional powers of the operator script A. And once we get there, this first estimate holds, and therefore we can apply Grongow inequality and obtain and conclude that solutions are zero in a local time, which can be and then this process can be iterated in order to obtain new solutions in the whole interval. Okay, so at this point we have this this flow with respect to the weak topology. Next is to obtain the energy identity. That's the next step. So in the case in which we know that the energy inequality holds for every weak solutions. So in the case in which we do not have boundary dissipations for the wave, then we can use an argument of time reversibility, which allows us to recover the reverse inequality and therefore the energy identity. And in the case in which the dissipation acts over the plate, we recover the energy identity by means of a finite difference argument, which was given in this article from Lashevska and Koch from 2002. So the basic idea is to work with the variational problem, and instead of multiplying your variational problem by z, by zt, we multiply by this difference here. My apologies. It's not z under t here. It's not time derivative. It was supposed to be h, which is the size of your mesh. Okay, so we multiply by this term and do computations, and we pass the limit in the remaining terms using proposition 4.3 in their article. Yeah, so in that case, we have uniqueness. We have energy identity for weak solutions. However, we still need the continuous dependence, which will follow in these two particular cases regarding the boundary dissipation. It will follow by means of exploiting the energy identity, the lower semi-continuity of the energy functional, as well as compactness of this embedding, and also the capacity of these applications here. And with that, we can pass to the limit and recover the continuous dependence with respect to strong solutions. And finally, in order to obtain more regular solutions, we differentiate the problem. So we differentiate the variational problem applied to Galerkin approximations, and then many terms can come from there. And the most interesting thing there is some terms like this one, which like this integral here, for instance, will appear. This is the most critical one, and it is critical because it returns us these terms cannot be controlled depending on your choices of boundary conditions, especially free boundary conditions. This term cannot be controlled by the energy functional. So it requires a more peculiar approach. So we use Verzigalwe inequality in order to derive this inequality, which still requires estimates for the H3 norm of these approximated solutions. And these we estimate this H3 norm using in the particular case, for instance, in the particular case of free boundary conditions, we estimate this H3 norm by means of exploiting fractional powers of this associated script operator A. And we obtain an estimate like this, in which W is the derivative of our solution. Yeah, so the conclusion of this regularity result will then follow by showing that by finding estimates in regarding second time derivatives of the solutions in the initial in the time t equals 0. These are few issues that appear in this step. So we have this critical unboundedness, which for which we work with we use control of logarithm Sobolev embeddings. And also another important issue is the fact that the Galerkin approximations, for instance, they do not yield H4 regularity. And in order to cope with this issue, we need to work with a specific basis of basis for our approximate space. Well, yeah, so that's our well-posedness result. So as I mentioned in the well-posedness results, we get a flow which is continuous with respect to weak topology for any in any case of boundary dissipation, and we recover a flow which is continuous with respect to the strong topology in the case where the boundary dissipation is in the case in which we do not have boundary dissipation, or the boundary dissipation acts over the plate in this particular case. So what happens? So the next step would be to study then the stabilization of the problem, and our preliminary results shows that we can recover stabilization in order to, we study the stabilization in this particular case in which we do not consider internal dissipation. We consider the particular case in which the boundary conditions are supposed to be claimed, and also the nonlinear function f has this very simple linear form. Okay. And our preliminary results are the following. We obtain a strong stabilization in the case of the system, in the case in which the boundary dissipation in the acoustic medium acts over the plate, and also with some relation between the coefficients. So the strategy there is quite usual. We define this Lyapunov functional, which allows us to conclude that the system is gradient using this relationship, these relations between the coefficients. And later we show that we extend we boost the weak convergence to the strong one in order to conclude that the strong stabilization. Okay, so what happens if the boundary dissipation does not act over the plate? So we have this we consider this particular case in which we allow the boundary dissipation to act on gamma 1, but only in the either in the whole portion of gamma 1 or in or with exception of a convex portion of it, which are called gamma 2. So in order to solve the problem in this case, we need a particular field that will localize this boundary dissipation. So in this case here, we are dealing with a weakly continuous dynamical system because the boundary dissipation is not all over the plate anymore. And also, when we explore this problem, we have these non-observed Neumann traces for the wave equation. And the result that we get is this one. We assume that the boundary dissipation acts over gamma 1, or except in the whole gamma 1, or except in a convex portion of it. We also assume the relation between the coefficients, and in that case, we recover the uniform stabilization. And the main ingredients for this result is to use these these two multipliers here, in which the field H is built having in mind this this configuration for the ports for the boundary. More details on the construction of this vector field can be found, for instance, in Lasiecka and Levitsik from 2000. And basically, the strategy here is to reconstruct the energy. So we reconstruct the energy for the wave, and then we reconstruct the energy for the plate. And as we can see here, for the energy of the wave, we have tangential derivatives that will, based on the choice of the vector field, we recover dissipating terms, and also terms that will be given by the coupling term. So these tangential derivatives needs to be dealt with, and for that we use results on Lasiecka and Levitsik also. And combining these two reconstruction, we obtain we reconstruct the energy for the whole system. Okay, and on the right side we get only the dissipation and the lower order terms, which can be absorbed by the damping term, and therefore the procedure after that is standard, and we get the uniform stabilization. The last comments here, as I mentioned, the tangential derivatives needs to be dealt with, and for that we use the estimates given by Lasiecka and Levitsik in this article from 2002, for instance, and also we need the sharp regularity results for the traces in the case of non-Lopatinsky condition. And for that, we have this paper from Tataru from 98, which was crucial here. These are a few references mentioned in this work, and I think that's it. Thank you for your attention.
Thank you very much. I think we don't have a lot of time, but if you have one or two questions, please go ahead. No? It's the first time I hear about Sedensko's method. Do you have any other reference about it?
Yes, sure. We have, for instance, let me see here, this article from Professor Lasiecka from 2006, for instance, they apply Sedensko's method also for the plate equation. Okay. And it's a good reference for it, for instance. And also, I'm sure that we can find more inside this one.
Okay, thank you very much.
Sure.
Somebody has a question, comment? Yes, Sylvain?
Yes, if I may, so it's mainly a question of curiosity. So you were mentioning this article by Tataru, where he discussed the case of non-Lopatinsky boundary conditions. What is the result in this case? Do we have a clear picture of what happens for the Cauchy theory and so on?
Well, in this case, we assume that the boundary, that the wave equation has Neumann boundary conditions. So, these Neumann boundary conditions are over the whole boundary. So, it's a case in which it's a case of non-Lopatinsky conditions in that case. Mm-hmm. So, when we compute when we use the multipliers, we end up having some boundary terms, and in order to estimate these boundary terms, we need this sharp regularity from Tataru.
Okay, yeah, I understand that, but how do I put it? In Lopatinsky cases, you have some expected result, right? and we know precisely what is the correct functional setting for the Cauchy theory. In cases in which you do not have Lopatinsky conditions, so typically the wave equation with non-homogeneous Neumann boundary conditions. Well, I've read this article a very long time ago, but I thought that at the end it was depending on the shape of the body and so on. No.
Yes, which is which is our case here. We consider this the shape of our domain is the dissipation acts in the boundary gamma 1, except in this convex portion probably. So the construction of this vector field is done by having in mind this geometry. Yeah. So in this case of non-Lopatinsky condition, we might not have regularity enough for the time derivatives on boundary. So we need to deal with these traces in another way.
Okay. Thank you.
Okay, thank you very much again. I
have, please, I have a question.
Yes, Omar.
Thank you very much. Thank you for your interesting talk. I have a question about the boundary condition you consider. If I understood, you consider also the dynamic because you have a time derivative in the boundary, right?
Yes.
My question is, can you consider a more general form of dynamic, for example, dynamic boundary conditions, where we have, for example, the Beltrami Laplacian?
We haven't considered this one. For the well-posedness, we have considered only the 3 classical ones, clamped, simply supported in the free boundary conditions. And for stabilization, we focus on the particular one, which was the clamped one. So we haven't considered any other type of boundary conditions so far. Well, there's still many questions to be answered regarding this model.
Okay, thank you.
You're welcome.
Okay, thank you very much, Jose. Now we switch to the next talk. So, Cristhian, can you share your screen, Cristhian?
Now you can see my screen.
Yes. So it's a pleasure to present Cristhian Montoya that now is, I don't know where, but he's going to Mexico at the end of the year. And his talk is on robust control and Stackelberg strategies for a 4-order parabolic equation. I don't see the title completely. So there's something blue in the screen that...
It's in blue.
Yes, compartir archivos con los demás, puede enviar archivos para que otras personas los visualicen o revisen. So something, I don't know if maybe you can put the screen, si lo pones en pantalla completa. Yes, now it's okay. Pero no. se ven los marcadores del lado izquierdo y estás en la segunda hoja ahora. Ahora estás en la primera. That's okay.
No, pero no estoy en modo completo.
No.
Ahí.
No.
Algo pasa, no lo sé.
Al parecer cuando lo pones en modo presentación se bloquea y ya no vemos, lo vemos mal. Ahí lo estamos viendo razonablemente bien, yo creo.
Sí, yo creo que puedes con eso. Se ve bien. Yes.
Okay. Thank you so much, Luz, for your invitation. Also, Alberto and Silvan. Okay, the main idea in this talk is to present a new or recent concept in control theory using the notions of hierarchical control, robust control, for a specific four-order parabolic equation called Kuramoto-Sivashinsky, with theoretical results and numerical examples. So the first one, we study the hierarchical control definition. Okay, this is a concept come from game theory with the first work by Kramer and Bernoulli in the 18th century, and also is related with, as we know recently, about Nash equilibrium, with some papers obviously given by John von Neumann, Morgenstern, and Nash. But in this talk, we only talk about Stackelberg strategy. That means that in our game, we only put two players. One player is called the leader, and another one is called the follower. And the game consists that the first player, the leader, has a movement, and the second one reacts trying to win or optimize the response given by the first one, by the leader. From a mathematical point of view, we can analyze this situation in this example given by Lyon. So we put two forces on the right-hand side. This is a linear heat equation. H represents the leader control, where omega small is the support of H, and V is the follower control. Okay, what is the idea in order to solve this problem? So first of all, we fix the leader, H, and we solve an optimization problem related to the follower. Okay, Y represents the state, YD is a target, OD is the domain related to the target, but for this talk we can consider the complete domain omega. This is a general domain in Rn. So we want to minimize this functional. This is linear, so it's not so complicated. Beta represents the Tikhonov penalization term, the constant, sorry. Okay, and once we have this control V, we analyze a controllability problem related with the leader control H. In this example, it's about the null controllability property. That means that we want to find a control H in some space, satisfy that the final state, the state of final time is 0. Okay, how to do that? Okay, the first part is classical, using convex analysis. So this functional is good in some sense because satisfy the continuous is continuous, strictly convex, and coercive. So with that hypothesis, we can guarantee the existence and uniqueness for the control V. Okay? And also is characterized by the expression in red color, P, and P satisfy the dual system. So this is classical setting. But now we have a characterization for the control V given by another system. Okay, with that information, we put together the primal and dual system, okay, in a couple system, in a couple manner. And now for this couple heat system, we need to find a function H, a unique control, okay, H. satisfy the null controllability property. So first, Leon in 1994 proved that it's not exactly null controllable, but it's approximately controllable. So that means that we are near to the zero in a capital time. But more recently, Araruna and his collaborators proving that null controllability property for the heat equation for this coupled system, assuming some hypothesis given in this box, where rho square is an appropriate function, which comes from the methodology. The methodology was Kahneman estimates. Okay, here I put some reference in different contexts for the heat equation, wave equation, also in fluid dynamics, micropolar fluids, parabolic equations, and more recently, in 2019, for this is what is related with my research for the Kuramoto-Sivashinsky equation. They prove not only the Stackelberg strategy, even they have some results for the Nash-Stackelberg controllability. That means that they consider several players. Okay, I suppose that there are more results in this context about hierarchical control. Okay, in summary, we analyze a system with two players. Okay? One is called the leader and another one is called the follower. The second topic is related to the robust control notion, and essentially the robustness in a system, of course, is the sensitivity that are not considered in the analysis and design. For example, when we put into the system disturbance signals and noise measurements that I show you here in this simple diagram. And the main idea is to create a game, another game, but now between the controller and the disturbance signal. In the following sense, we want to find this pair, controller and disturbance, in a simultaneous manner, but with different role. We want to find a disturbance signals which stabilize the system, but simultaneously a minimum controller stabilizing the system. Okay, which means in a mathematical point of view, we need to find a saddle point between the controller and the disturbance signal. Okay. Okay, and now the mix between these two concepts in only one that we call robust Stackelberg controllability. This is a general framework where Y represents the state. This is a system one is a general situation where A is a linear operator and N can be a nonlinear part. On the right-hand side, we have three forces. H will be the leader control, B is the follower, and psi is the disturbance signal. Okay, so we can see that when H or V is equal to 0, only one, we have a robust control situations. But when we put phi equal to 0, we can analyze the system in the framework of Stackelberg strategy. But now when we have three forces in this right-hand side, we need to create some strategy for analyze these three terms. So now the game is to fix the leader, H will be the leader, and for the V and psi, we find a robust control. We solve a robust control problem, exactly. And then we apply some controllability strategy for the leader. Can be null controllability, approximate controllability, or as a controllability if we can, of course. So our model is this four-order parabolic equation that I mentioned before. Okay, the state is related to reaction diffusion processes. The fourth derivative is the dissipative term, but in a more physically represent a dissipative phenomenon, but in a smaller scales. Meanwhile, the second term is related to some stabilities, but in large scales. And finally, this nonlinear term is a transferring term between energies from small and large scales. This is a simple simulation using finite elements, but okay, I have some comments about what kind of elements we can use in an efficient form. Okay, so now we put three forces, the right-hand side, H, B, and psi. As I mentioned before, H is the leader, B the control, and psi the perturbation. So the first step consists in finding the saddle point. So we fix H in L2, and we consider this functional, okay, in Hilbert spaces. So this L square is the parameter for the control. Meanwhile, gamma square with this minus is the parameter related to the disturbance. Okay, so we need to prove a min-max inequality between B and psi. How to do that? Using convex, and this is using this theorem. This is classical in convex analysis. So we need to prove the concave property and upper continuously, semi-continuously for the disturbance signals. And in a similar way, we need to prove the convexity for the follower, and as well as a lower semi-continuous property for the follower. Okay, some limits. This is normal situation, but essentially with these four assumptions, we can guarantee the existence a uniqueness of a saddle point, V bar and psi bar. In general, this is classic, but it's not so easy because now we have a nonlinear system. So we need to take several estimates, energy estimates, trying this nonlinear part. And some assumptions, of course, respect to the initial data. Okay, in summary, when these parameters gamma and L are large enough and small datum, as mentioned before, we can find a saddle point V bar and psi bar given by this expression in red color, which C satisfies and the adjoint system. Okay, but it's important that you can see the saddle point is not the same, but it's almost the same. Maybe there are some different respect to this subset, C omega, the parameters of course, but it's almost the same. Okay. Okay, in norm, it's almost the same if we consider the same parameters L and gamma. Okay, and the next step will be to find this function h related with the system tree. It's a coupled system, so that means that we want to control this coupled system for order parabolic nonlinear equation using only one control. But here, once we have the characterization for the robust control problem, this parameter L and gamma will be very important in the analysis. Okay, now, as we know, first we analyze the linear system related to the system tree. And our strategy was Kahneman estimates for this observability system. Okay. Okay, in this talk I don't explain about Kahneman estimate. There are several experts in this topic in the seminar, but essentially the important there is this in blue color. That means that we can make observability inequality observing exactly only one state, the first state associated to the observability system. Okay, the different rows are Kahneman weight functions. Okay, I'm putting together this information just for the linear part. We can pass using some fixed mapping theorem to the nonlinearity part. And with all this information, we can guarantee the existence with respect to the saddle point, V bar and psi bar, and also the null controllability property for the Kuramoto-Sivashinsky equation. Here we have similar hypotheses like Araruna in 2015. The same, we need to impose that this there is integrable. Okay, rho is again appropriate weight function given by the Kahneman estimates and a small initial datum. This hypothesis, respect to the initial datum, is given for the fixes mapping theorem and also for the robust control problem. Okay, the result is under review in this moment, and it was done in collaboration with Louis Breton. Louis Breton is a PhD student from UNAM, Mexico City. As far as I know, I only find the result in this context using this combination between robust control, hierarchical control in only one notion. And the first work was done by Victor Hernandez, Luz de Teresa, related with the linear and semilinear heat equation. Next, we extend that result in collaboration with Luz for the Navier-Stokes equation. And more recently, Victor again with Liliana Peralta have making some observation for the heat equation, but change the controls now on the boundary conditions. This is essentially the information respect to the theoretical part. That means we have three forces. Two forces are related with the robust control, and one force, the leader, is associated to the controllability process. For the numerical part, we only describe the scheme for the people with some knowledge in a theoretical framework. we use a theta scheme at Balfour. That means that we have two levels in time, not only one. It's a two-level method in time, and we only use P1 final elements in space, even when we have four derivatives. So why? Because we have some change of variables, and in that article we only prove that this numerical scheme works without a convergence range, but okay. And in this table we show that the numerical scheme holds for different time steps when we fix a number of nodes in the space in two nodes, L infinity and L2, and the opposite. We fix the time steps and different size respect to the mesh for the space. Okay, we have two examples in this slide respect to the robust control. Every row is an example. So the first row, we have the disturbance functions psi1 and also the control function big1. So you can see a similar behavior with opposite sign. So for a first configuration. And now the second row is when we consider the control function with a support in minus 10, 10. Okay, it's almost the same, but just is the control function is localized in the symmetric interval. Okay, how to do that? So if we see inside of the numerical part, we need to use the Hilbert unionist method and also know the classical conjugate gradient method. Instead of, we need a nonlinear conjugate gradient method for solving our problem. And respect to the robust Stackelberg controllability, this is an example with different domains for the leader, omega small, for the follower, okay, and a small initial data. Yes. Even we have some results when the domains between the leader and the control is not empty, but we don't have a theoretical response to that situation at this moment. And finally, some open problems in this direction is about to put maybe the leader on the boundary condition or another one, and also extend the possibilities by considering only two forces and consider the Stackelberg strategy. That means several players. And of course, the application of this notion to other models. And maybe we can find another numerical scheme or method for solving the robust controllability problem. That's all. Thank you for your attention.
Cristhian, thank you very much. Are there any comments or questions?
I have a question.
Yes, please.
Just for curiosity, Which will be the problem for your first open problem? For instance, if the leader is acting in the boundary, no? This is the
okay, this is one possibility to extend our result if the leader is located on the boundary.
But a priori, I guess that there is no, there seems to be no problem, no obstacle about this. Or what do you think?
Well, let me see.
I'm not sure, of course.
Me too, but so you know, we need to create, if we follow this direction, we need to create a Kalman estimate when we can see the behavior of this leader, of course. But we can try that in the future, but essentially is to create a new Kalman estimate, of course.
Yeah, I guess.
How? I don't know, maybe we need to review the literature about Kalman estimates for this fourth-order parabolic equation with local terms, but on the boundary, of course. But to be honest, I don't know. I think that first we need to review, for example, the work by Victor. Victor has some results for the heat equation with controls on the boundary condition. So maybe this will be the first step or the zero step, really. And also, yes, you have some results, you, Alberto, with Eduardo Serpa.
Yeah,
for the
Kuramoto-Sivashinsky
questions.
In the boundary.
Yeah.
Okay, well, maybe we can discuss also later. Thank you,
Victor
Cristhian.
is in the audience. Maybe he can say something about it. I don't know. Victor,
Yeah, I don't have a lot of experience with boundary conditions.
Can you hear me?
Yeah.
Yes.
Okay. Related to Alberto's question, one of the problems is that you have to prove an observability inequality for two equations with only one observation at the boundary. So if you apply, for instance, the known Kalman estimates with boundary observations, then you have to eliminate one of the observations. The problem is that you don't have a way to do it like in the classical works where you do local energy estimates. You need to do some extra efforts to do the things. So right now I cannot remember what we did in that work exactly, but I remember that when you have, for instance, everything on the boundary, leader and followers, you need to add some extra weights, exponentially decaying weights to the minimization problems, and those weights help you, but it is not as straightforward as in the, let's say, internal case. And also, these results are not as good as those, because you need to impose extra conditions, and it's simplifying the problem. I don't know if in the case of Cristhian, where he has a very general nonlinear equation, we can extend those results, but maybe it is worth to try, but I don't know.
Thank you, Victor. Omar is raising the hand. Please, Omar.
Okay, thank you very much. I have a question.
Yes.
I have a question about the assumption on the target YD in the main results. In your main results, if I understood, your target YD have to be in a weight space and L2 with a weight.
Yeah.
Yes, right? My question is, can we construct some target which makes the optimality system uncontrollable? That is, what about the optimality of this condition?
I don't understand exactly the question when you say the optimality condition for these target functions. Maybe it can be.
Yes, I
can precise the.
If I understood your result is true with this condition. That is we don't have the result with any target in L2, for example. Yes or no?
Yes, that's right. No, any target. Yeah, it's for any target. Yeah, it's for any target.
In my eyes, to look for some target which make the system, the optimality system, uncontrollable. You know what I mean?
I think this is a very good question, and it happens also when, for example, for a single hit equation, you want to control the equation with a right-hand side term. You ask the same kind of property for this right-hand side needs to have a particular decay, exponential decay at capital T. And we really don't know if this happens due to the technique, that is this Kahneman inequality, or is really necessary. I think in my experience, I can think this is necessary, but nobody has proven. Okay, so I don't know a counterexample. I don't know if some people has done some numerical experiments and maybe try to see if it's not possible to drive the solution to zero. I don't know, but it's a very interesting question. I think in several contexts, it's not only in the case of a Stackelberg strategy. This appears in several situations, and I don't know if it is related to the Kahneman estimate or really it's a condition necessary. I don't know.
Thank you very much.
Okay, so Victor says that we need numerical experiments in the sensitizing case. There, the source term should decay exponentially, and numerically, it seems that it is indeed necessary, the decay. So yes, I think I agree with Victor, no? So this kind of problems appears in several situations, and as he says, with numerical experiments, they have the feeling that this is necessary. But I don't know if somebody has a counterexample, for example. I don't know. So, okay, I think it's very late. So thank you very much for your two nice talks. Please send us the slides to put in the website. And I recall you that we have 2 more sessions of the webinar before summer and how do you say, and winter holidays, because we are everywhere, no?
Yeah.
So it's a winter vacation in the South Hemisphere and summer vacation in the North Hemisphere.